Hello, everybody, and welcome to my talk. I'm Stefan Richter, and I work as a software engineer at Data Artisans, and I'm a Flink committer, and I'm mostly working on all state-related things in Flink, like state backends, checkpointing, and rescaling. So in this talk, I will essentially mainly give you a deep dive about incremental checkpointing in Flink, because from the feedback, I figured out that might be the topic that you guys are most interested in about improvements for large state. So, but first of all, I want to give a little bit of context. So first, the question, what is state in streaming programs? So I have a small example here of a streaming program that is basically taking events and has a map function with state that runs like a streaming state machine that's generating alerts in some cases. Then the alerts get filtered, and we want to filter for all critical alerts and basically, count how many count in a window how many times we see a certain alert message. So in this small program, we see stateless operators and stateful operators. So for example, obviously the state machine is a stateful operator, and also the window is a stateful operator. So if you want to combine state with stream processing, we have basically two fundamental different approaches how we can do that. One which I would characterize as internal, and one that I would characterize as external state. For external state, I mean that we keep the state in a separate state store, and that, for example, like a Redis database. But given the characteristic how the stream processor typically processes events and queries the state, this is a very slow solution, because typically we're following a get-put pattern where we receive an event and we want to get the state under the key of the event, modify the state, and write it back to the store. So every time we need to take a round trip to this external store. On the good side is that the store is, in this case, independent from the stream processor. So even if the Flink job goes down, we can still query the state, which is also related to what Ufuk just presented to you. And what is also important to know is that with external storage, it's a lot harder to get exactly once guarantees, because it has to be supported by your store, for example, through transactions. And it has to be tightly coupled with how Flink is failing and rolling back the state of a program. This is why the approach that we use in Flink is internal state. So we are keeping the state in the stream processor, because this is a lot faster than external state. So what we are doing is basically the working area of the state is inside, for example, the heap of the JVM or on the disk. So it's definitely local to where the computation is run. And again, a disadvantage over the external state is that we need to take care of checkpointing ourselves. So basically, all our operations are done locally in memory or on local disk, and checkpointing then go to some stable storage, like some distributed file system. And with this approach, we can also always have exactly once consistency, because it's completely under our control when we do our checkpoints and rolling back to a certain checkpoints. And also the stream processor itself is able to handle scalability. So as for the implementations of state backends in Flink, right now we have two different state backends, which have slightly different characteristics. On the one hand, we have a heap-based implementation where all the state lives on the Java heap, and Flink operates directly on objects on that heap. So the underlying implementation of that state backend, you can think about it like a Java hash map, basically, where the key in the hash map is the key of your event, and the value is basically the state for that key. On the other side, we have an implementation that is based on RocksDB. For this state backend, the state lives off the heap, and it can also go to disk. So benefit of that is we can support states that are much larger than the size of the memory of your machine. And also we avoid getting caught by garbage collection, because all the state is in off-heap memory. So in contrast to the heap keyed state backend, this backend operates with bytes. So basically, think about it like an embedded key value store where you can just basically put and get byte keys and byte values. So it always, so again, in contrast to the heap keyed state backend, you always have to go through serialization every time you have a put and a get to that state backend. RocksDB is based on a log structured merge tree, which comes in very handy for certain features, which I will explain briefly. And what RocksDB is also natively supporting is asynchronous snapshots. So that is also because of how this log structured merge tree works. So for the upcoming release, we have 2 new features that we want to introduce. One for the heap keyed state backend, for which we also now offer asynchronous support, and incremental snapshots for the RocksDB keyed state backend. So at this moment, I briefly want to talk about the importance of asynchronous checkpoints. So, for example, why did we introduce asynchronous checkpoints now also for the heap keyed state backend? This was basically driven by a user request. So what we had were users that basically have a relatively small state, but they want to access it at the fastest possible rate. So, which is why they would typically go for the heap state backend to avoid the serialization issue. Because if they switch to RocksDB, what they observe is basically that most of their CPU cycles are burned in serialization. However, there is a problem with if you have checkpointing without asynchronous, if you have synchronous checkpointing. And that is, as you can see in the graphic, basically you have an event processing thread that is the loop which processes the elements. And at some point, a checkpoint coordinator thread that runs on the job master is deciding that it wants to trigger a checkpoint. A checkpointing thread is listening for that request. And once the request comes in, it basically holds the event processing thread and starts writing the complete state at this point in time to disk. And afterwards, it will acknowledge the checkpoint and stream processing can go on. So now you could say, okay, I have all my state in the heap, so this should not be too much of a problem. But what many people are not aware of is that writing the state against the distributed file system means that you're interacting with some remote system which can behave in arbitrarily bad ways. So for example, this call could basically block forever, which we, for example, observed when interacting with S3, and then we had some quota exceeded, and basically this call would block forever silently, and the job will fail in some very bad way. So the idea of asynchronous checkpointing is that once you receive the trigger from the checkpoint coordinator, you only spend a small time in the event processing thread to generate a snapshot, and then basically use the snapshot to write your state to disk. So the only problem in this case is how do you deal with concurrent modifications? So that means you need a data structure which has some support for taking snapshots, like multi-version concurrency control and so on. Otherwise, the changes that the stream processor will do in the meantime would reflect into your state, and you would write corrupt or inconsistent state to disk. And this is why we had to introduce asynchronous snapshots also to the heap keyed state backend. Okay, but now let me come to the incremental checkpoints. So what I want to discuss is, first of all, what are incremental checkpoints? So what is the basic idea? And then give you the intuition why RocksDB is so particularly well suited for what we want to do with incremental checkpoints in Flink. And last but not least, I also want to talk about how this actual integration with Flink's previous checkpointing mechanism is happening. So I also want to mention that this development is basically driven by Alibaba and by data artisans. So the idea how this works is follows. So first, without incremental checkpoints, what you basically have is that checkpoints are triggered at a certain point in time. And at that point in time, you see a certain state which goes one-to-one into the checkpoint. So imagine you have a state size of a couple of hundreds of gigabytes or maybe even terabytes. That means on each and every checkpoint, you need to write your whole state to a distributed file system. Of course, this is rather wasteful, and you could think about something like this. So basically, every time a checkpoint is triggered, you're only considering the delta, so the changes of what has from the previous checkpoint to your current checkpoint. And that, of course, can be a lot smaller than always writing a full checkpoint. However, what will happen in case of recovery is that you need to consider all the increments. So basically, if we want to recover the third state, what we need to do is we need to apply the incremental checkpoint 1, apply incremental checkpoint 2, and apply incremental checkpoint 3 on top. So basically, with that method, the number of increments could grow indefinitely over time. So what you would naively do is at some point in time, you take a full checkpoint, which then serves as your base for the next increments and drop all the old increments. This is where some features in RocksDB come in very handy, which I want to give some short and simplified overview of how RocksDB works. So basically, you can think of it like two tiers. First of all, you have a memory table, which is held in memory, and all writes go against this memory table. This works like a mutable buffer, and the size of this mem table is only just a couple of megabytes. This mem table is periodically flushed to stable storage, and then it becomes immutable. This is very important. And the structure that you have on disk is basically you have key value pairs that are sorted by keys. So the first thing that is interesting here is that even if you have a couple of updates for the same key, once it's flushed as a mem table, as a SS table, all keys become unique, and you only see the latest modification of that key reflected in the SS table. So what's also very interesting is if you consider that those periodically flushed mem tables appear over time, we can consider all SS tables that would appear between two checkpoints like as the delta between two checkpoints, and can use that for our incremental checkpointing mechanism. Another thing that's very interesting is that RocksDB is also performing compaction in the background. So that means there is a background thread that merges SS tables on disk and thereby basically consolidates them. So you take two tables, and basically what is reflected in the merge table is just the latest version of the state for each key. So through this mechanism, we basically get something that is also consolidating our deltas over time. Okay, now I would like to explain to you how this is basically how we integrate this with Flink's checkpointing. What you see in this graphic is, first of all, you have three stateful map operators. Three instances of one stateful map operator, and each has its local instance of RocksDB. Then there's the checkpoint coordinator, which has something that is called a shared state registry, which we newly introduced. So in the first step, like with the normal checkpointing mechanism in Flink, the checkpoint coordinator is triggering a checkpoint on all the instances of the stateful operator, and the stateful operator reacts in the incremental case by emitting the deltas. So I now want to take a look at one instance of that operator to explain to you how we figure out what is the delta that we want to emit. So if we peek into that instance of the operator, what we can see is some local file system which contains a data directory of RocksDB. The data directory of RocksDB consists of some manifest metadata file, which is mutable, and the flushed SS tables, so the immutable SS tables, like I explained to you before. And the second component that we have here is some folder in a distributed file system that we call a shared folder, and it is under a path that is specific to that operator and then also to the instance of the operator. What now happens is we use RocksDB's native checkpointing mechanism, which will trigger a copy of the manifest, and it will also do hard links to the SS tables in a checkpointing directory. So since the SS tables are immutable, hard links are enough in this case. So because they're not modified, but we need to hard link them because they might become subject to compaction and get removed while we want to write our snapshot. In the next step, basically we need to figure out which SS tables we need to transfer to the shared area. So we want to transfer all the SS tables that are not yet in the shared space, which in this case, since we started with the first checkpoint, we transfer both SS tables 225 and 226. This is becoming a shared area that is shared across several incremental checkpoints. Then there's also a private state to that checkpoint, which goes to a private directory, and it consists of the manifest, because the manifest, as you remember, is mutable. And it consists of a list of references to the SS table. So basically this list would contain now the file names for the 225 and 226 SS table. And this upload to HDFS can be done completely asynchronously. After the upload is done, each stateful map operator instance will send an acknowledgement message to the checkpoint coordinator, and this acknowledgement message contains something that we call state handle, which is basically, like in this example, a path to the files in the distributed file system. From this state handle, the checkpoint coordinator can figure out which files were introduced to the shared directory and do a reference counting of those files in the shared state registry. So basically the shared state registry is a reference counter. How many incremental checkpoints are referencing this SS table? So in this case, it's just checkpoint 1 referencing those 2 SS tables. So now there's a fourth step in this process, which is different from the normal Flink checkpointing mechanism. And that is, after the checkpoint is completed successfully, the checkpoint coordinator also has to signal to the operators that the checkpoint was actually successful. So why is this important? Because if the checkpoint would fail, the checkpoint coordinator would react in the way that it will delete the files that are no longer used, which could mean if there was a newly uploaded SS table by one operator that's only referenced by one checkpoint, and the checkpoint fails, the checkpoint coordinator would be allowed to remove that file. But the operator itself could still assume that the checkpoint was successful and build future increments under the assumption that the SS table was uploaded in a successful previous checkpoint. And to prevent this, we need to explicitly acknowledge back to the operator that the checkpoint was actually successful. So what will happen if another checkpoint is triggered? And we can actually see some incremental things going on. So after some processing, we see that the local file system, the data directory of RocksDB in the local file system changed. So for example, state table 225 that was previously there is no longer there, but there are also 2 new state tables, 228 and 229. So we could assume maybe that something happened that state table 225 and 227 got merged. So then again, we trigger the native RocksDB checkpoint. And now comes the interesting part. From the acknowledge message that we got from the checkpoint coordinator, we already know which files are acknowledged to be already present in the shared directory. And now we will only upload the missing files, the missing SS table files, which are in this case 228 and 229. At the same time, if we go back to the shared state registry, we see that we have new entries of the newly referenced files, in particular 228 and 229, which are only referenced by checkpoint 2, but 226 is referenced now by checkpoint 1 and checkpoint 2. This is important if we want to delete incremental checkpoints. Now, assume we only have a window that we always want to keep one incremental checkpoint at a time. So that means after checkpoint 2 is completed, we want to delete checkpoint number 1. So what will happen is that we delete the private directory of checkpoint number 1 and go through the SS table list that is that we find in this checkpoint directory. With that, we basically modify the reference count in the shared state registry, so we can see that there's no longer any reference to SS table 225, which means that we can remove it from the shared space and from the shared state registry. And this way, the whole incremental checkpointing mechanism is basically also kind of self-consolidating. So you don't have an you don't have an infinite amount of increments piling up. Okay, so wrapping this up, we've seen that incremental checkpoints can dramatically reduce the checkpointing overhead for very large state, and that incremental checkpoints are also async, which is very important for the reason that I explained. RocksDB Compaction helps us to consolidate the increments and keeps also the overhead low in case of a recovery, because we don't have to go to a large amount of increments. There are also current limitations in this incremental checkpoints for Flink. In particular, it somehow breaks the unification that we previously had between checkpoints and save points. So right now, with this incremental checkpoints, we would consider checkpoints something that is more of a low overhead in compared to save points, which is a higher overhead because it's taking a complete checkpoint, but it has also some certain additional features. In particular, we can rescale from a save point, but we can no longer, or currently at least, we can no longer rescale from an incremental checkpoint. Then I briefly want to mention further improvements that we do for large scale in Flink 1.3, and also parts of that might go in 1.4. So I've already mentioned the async heap keyed state backend, which is already merged. Then there's also the corresponding async heap operator state backend, for which there exists an open pull request. We have a map state, which is basically an improvement over over having like a hash map in a value state, which is very hard to use for in-place updates. So for example, if you imagine under a key, there is a hash map that gets always serialized and deserialized to RocksDB, even if you only want to modify one key inside that hash map, that has a very high overhead, so which is why we introduced the map state. So, and map state is also already merged to master. And for the future, so I think those things will go more into Flink 1.4. We also have another type of state, which is the timer service, and we will introduce a timer service that is backed by RocksDB. And we want to make the current timer service, so the heap internal timer service, also asynchronous. So that's it for my talk. And yeah, if you have any questions. Okay.
Where the shared state registry saved?
Sorry?
The shared state registry, is it in persistent storage or is it in memory somewhere?
That's an interesting question. So it is only in memory of the job manager. But in case of a job manager failure, it's very easy to recover, because basically what the job manager can do, you just go through the to those SS table list files, scan the files, and just recreate the counts from the present SS table list files.
Great talk, by the way. When you make basically the checkpoint, the copy of the manifest and the hard links, how do you make sure that that's consistent?
That is because this mechanism is provided by RocksDB itself. So it's just something that you call, and RocksDB itself will provide the consistency guarantees. Okay, and then the actual using those files directly that RocksDB is managing, is that a supported API from RocksDB? Yes. Okay, thanks. There's one more in the back. One more in the back, I think.
Yeah. Is incremental checkpoint in 1.2 or just 1.3, coming in 1.3?
It's coming in 1.3.
Maybe you answered it on the first question, but how do you transactionally update the shared state and then delete and clean up the files?
Basically, the update to the shared state registry. So the increase of increments goes with the acknowledgement. So basically, if the task sends the acknowledgement, it sends the state handle, right? And the state handle basically contains the information which counts to increase. And as for the deletes, this happens also because the checkpoint coordinator knows the state handle. It will trigger a delete on the state handle, and from the state handle, it can see the counts that it has to decrease. So it's all happening in the checkpoint coordinator, and that's why it's transactionally okay.
For the async state, async JVM heap backend, right?
Yeah.
Should we always pay that overhead of serialization and deserialization, even if we ensure our objects are immutable? Let's say like I have a list state, I have object 1, 2, 3. There is a checkpoint barrier, and 4, 5, 6 because it's like accumulating some state. Will Flink be smart, or is there any primitive or API support for me to mark something as, hey, immutable, you need not worry about, I need not pay the serialization and deserialization cost?
So first of all, I think it got mixed up a little bit maybe, but the distinct feature of the heap keyed state backend is that you don't need to go through serialization. You always work on the objects themselves, right? So, or if you're asking in specific about the async version of it, it's using the type serializer at some point in time to make copies of the state objects. So one could assume that this will use serialization, but the type serializer has actually a copy method, and the implementation for your type could consider that it's immutable and just return the reference that you pass to the copy method. So in that case, the copy is just the object itself.
Any other questions? You have 10 minutes. Okay. Thank you for the presentation.